I pulled a bit of a switcheroo. If you looked at the program up until about 3 hours ago, you would have thought I was talking about something else. But I didn't want to talk about the same thing I talked about at school. So instead, I'm going to talk about the final Kepler Catalogue. And first, I want to say I'm standing here on behalf of many people in the Kepler Science Office who've worked very hard on this final catalogue. So in no way should this be construed as all my work. It's a big collaboration. It's been a big project. So Dan actually started with the introduction to the Kepler mission, so we can breeze right through this. It's a telescope that was launched in 2009, a 1 meter telescope, and it was designed to measure Eta Earth. So that's how common planets like the Earth are. And even since the mission was designed, and even since it was launched, our definition of Earth-like has changed. As we've gotten more information about, for instance, this transition region between super Earths to super Earths to sub-Neptunes, what we think of as being Earth-like is evolving with time as we get more information. But Kepler was designed to find out how frequent rocky planets in the habitable zones of stars like the Sun were. It used the transit method, which Dan described, and everybody who was at the school knows all about now. It's the dip in brightness of a star as a planet goes in front of the star that you monitor the brightness of the star, and you see. And what Kepler did was monitor 200,000 stars for 4 years, looking for these dips. So what do you get when you send a 1 meter telescope into space? So this is a light curve of a hot Jupiter planet, a large gas giant in a 2 or 3 day orbit around a star. So this is a 10 centimeter telescope on the ground. This is 60 days of data phased up. You can see the transit, you can see it there, that's the planet going in front of the star. This is a single transit of a 1 meter telescope on the ground. You can see it there. Right? This is when you send a 1 meter telescope to space. This is 10 days of data on that same system, and that's actually the data. That's not a model. And that's exciting because now you can actually zoom in on the y-axis here and start to find other interesting things happening. You can actually see this is where the planet goes in front of the star and blocks the light. This is as the planet goes around behind the star, it starts reflecting light back like the phases of Venus. This is where the planet goes behind the star. So all these photons here are coming from the planet. We're actually measuring photons from the planet. And then this was just 10 days of data. When you have 4 years of data, you start to be able to look at that curve in even more detail and start to see different effects through reflection and emission. And now you're starting to talk about measuring the weather on the planet, which is really exciting. But this is just an aside to say Kepler's cool. All right, let's jump straight to the result, the final Kepler Catalogue. So in order to measure how common planets like the Earth are, we need a list of planets that Kepler's found. This is our list of planet candidates as of the final data release. So what I'm showing here is period on the x-axis and planetary radius in Earth radii on the y-axis. So 1 Earth radii at 365 days, so Earth lands around there. One of the first things you can see is that most of what Kepler found, this huge bulk of planets, is between 1 and 4 Earth radii. So that's between the size of the Earth and Neptune. And that's really interesting because there's nothing in our solar system between the size of Earth and Neptune. And most of what we found was between the size of Earth and Neptune. So that's led to these really interesting studies like Dan showed about mapping out this transition region from rocky planets to volatile rich planets. All enabled by the fact that we've just found thousands of planet candidates in space. There we go. Okay, but what we care about is Earth-like planets. And there's this big gap here. And we don't think that's physically real, that there are fewer planets here. It's the fact that our sensitivity has dropped off there. So in order to find out how many planets there, we need to measure to what extent our sensitivity has dropped off. So unfortunately, there's a little bit of jargon involved, so I'm going to walk you through my glossary. The pipeline, the Kepler pipeline, analyzes all of the data, so 200,000 stars, each of them has a 4-year light curve. The pipeline goes through and looks for periodic events. We need at least 3 events to call something a planet candidate. So the pipeline goes through and finds 34,000 out of the 200,000 light curves as some kind of periodic event that you could fit a transit to. We call those TCEs, threshold crossing events, the threshold being the signal to noise that it needed to achieve. Most of these are junk. One of the things I talked about yesterday was the fact that most planetary systems don't have transits. You need to be lined up the right way. So there's no way 34,000 out of 200,000, 1 in 6, is lined up the right way. So most of these are junk. We know that already, but now we have to work out how many of them are junk. So 34,000 TCEs come out of the final run of the pipeline. KOIs, separate object of interest. Those are the TCEs that look like actual astrophysical eclipses when you look at them. not necessarily caused by planets, they could be eclipsed and binary stars. These are the things that look genuinely like real astrophysical events that we want to look at more carefully. There were 8,000 of those in this final round pipeline, so 8,000 out of 200,000 stars. Planet candidate is when you take that list of astrophysical signals and you put them through a battery of tests we've talked about in order to determine whether you think that they're eclipsed and binaries or planets. So in the end, this final catalogue has 4,000 planet candidates, and that's what I plotted the previous slide. So what I'm showing here, DR25, data release 25 is the final catalogue. So the black line is all of the TCEs that came out of the pipeline. This is period again in log space, and this is the number of TCEs altogether. So you can see this drop off, which is happening at longer period, and that's fine because you expect, as I showed yesterday, this probability drops off with periods. You expect fewer things time to time. Then you see this big bulge here around 372 days, including a big spike right at 372 days. Does anybody know what 372 days is? It's the orbital period of the Kepler spacecraft. So either the universe really likes putting planets at 372 days, or these are all fake signals caused by the orbital period of the spacecraft.
Or being close to it.
Yes, or being close to it. So this is actually the exact orbital period of the spacecraft, and this is what happens when a bunch of gaps line up because of the fact that we have a regular download of data. So this is a whole bunch of gaps line up and you can make events that aren't real. So that's not real. So we need to work out how to take out background because what we care about is pretty close to that peak, right? That's a shame. We've got this giant spike right there. We need to work out how to get rid of it. So you might notice that the black curve has many more things at long periods than the green curve. The green curve was the previous catalogue. And that was because we knew this was the final run. And we wanted to let as many things through that could possibly turn out to be planets as possible. We were being very permissive. Anything that could conceivably get looked at and turned into a planet, we wanted to push through. So that we end up with a much larger list to choose from than if we had it constrained and kept some of the same tests we had in the previous version of the pipeline. Because some of these might be real. Most of them aren't, clearly, but some of them might be real. So we wanted to make sure we had as many as possible.
Does the y-axis count? You say counts, is that crossing events or is that candidates?
So this is still TCEs. This is still TCEs. So this is the 34,000 is being plotted here. Okay, so what do you do with your 34,000 TCEs? How do you find out which ones are junk? It used to be a group of people that would meet Tuesday morning at 10 a.m. and look at them. So when we started trying to do statistics, it was like, how do you quantify the statistics of a group of people at 10 a.m. on a Tuesday morning? Like some days you're going to be like, yes, everything's great, everything's a planet, oh, life is awesome. And some days, your paper got rejected or you got bad review, and you're sitting there like, nothing's real, it's all wrong, it's terrible. So that's not repeatable unless you want to get rejected every day. So what we did was to create an automated algorithm that mimics the decisions that humans are making when they looked at the light curve. So when you're looking at a light curve, you're actually making a set of decisions about the shape of the candidate, the reliability of it compared to the other signals in the light curve, and that kind of thing. So we basically just had to automate that. So we built the RoboBetter, and it's basically a set of decisions that get made on the light curve. I won't go into too much detail. The first is, are there any other TCEs that have the same period and epoch as this TCE? Unless the universe really likes putting things in the same period, the same transit midpoint, then those are probably spoofs. What happens is you get reflection, you get optical reflections, bright stars that have a eclipse and bright or something on them reflect up and down and end up on other stars. You get electronic ghosts, CCDs next to each other that are reading out at the same time. You get signals cross-talking with each other. So you get a bunch of signals that have the same period and the same epoch. Those aren't all real, so that's good, get rid of those. Another thing you can do straight away is Kepler's pointing was extremely precise, which is fantastic, because you can tell exquisitely to an incredible amount of detail where the transit signal is actually happening. You can tell whether it's happening on the star you think it's happening or happening nearby. So if it's happening nearby, then it's almost certainly a background eclipse and binary, two stars going around each other, creating an actual large dip that's being diluted by the target you think that the signal's around. So you can get rid of a whole bunch of things straight away where the transit signal is just not happening on the star. So now you're left with, okay, it's a signal that we think is real on the star. What kind of decisions do we make? The first one is a whole separate subtree that comes out. I'm going to boil it down to, is it transit-like? Is it unique in the data? When you look at the light curve, you see a whole bunch of other transits that look the same, but the light curve couldn't possibly have that many transits in it. Is it consistent? One of the most common forms of false positive is you have one deep event, which is maybe a systematic or something, that gets folded onto noise elsewhere in the light curve. So you end up with one deep thing and two shallow things, which when folded create a signal to noise that crosses your boundary, but they're actually not all the same depth. So you ask, are all of the events the same depth? And the other one is, this sounds a bit specious, but more than 50% of the data needs to be real data and not just fall into a gap. So when I was saying before, that big lump is caused by the fact that we have these gaps in the data at long periods. You have, one event, another event, a gap, some noise, and it's like, oh yeah, that's great, I have to this. But you can't have two events falling gaps if you're careful. More than 50% needs to be real data. Once you think it's a real astrophysical transit, then you start asking, is it an eclipsing binary? So one of the things you can look for is a secondary eclipse that's inconsistent with the planetary interpretation. The planet can't reflect more light than it's receiving, because otherwise it would be self-luminous and therefore it's a star. You can't have every other transit be a different depth from every other transit, because that implies it's two stars of different sizes. But this is really interesting. So one-to-one resonance, if they were different sized planets and they had the same period, they would get thrown out. We would never have found them.
I looked.
You looked? Okay. I was just sitting there like, wait, you have a test that deliberately excludes those. Okay, someone looked good. Okay. And then the other is the shape of the transit. So remember yesterday when I was describing transits, the canonical transit has a lovely U shape. But if it's two stars grazing each other, you get a very V-shaped transit. So you design a test which measures the V-ness of your transit and has some threshold. So there's a whole battery of tests that your signal has to pass in order to become a KOI and then a planet candidate. So we're back again at our list of TCEs. So we put those in the RoboVeta. Now, note that this y-axis of just counts is changing, okay? So it's changing to a max of 200, right? So we got rid of all of this short period stuff, which is mostly eclipsing binaries that are polluting the signals. And we got rid of a lot of this long period stuff has also gone away. We still have a little ghost of a spike here, and we still have these two things here, which actually you can see are quite bright here. These are eclipsing binary, bright eclipsing binaries that do this ephemeris matching all across the planet. You get heaps and heaps of pollution due to the fact that there are these bright eclipsing binaries that just reflect all over the place. Just consider them like bouncing around the CCD, like, whoa, whoa, whoa. And you end up with all of these signals with the same period. All right, so that's the KOIs, and then we decide which ones look like planets instead of EVs. So now the Y is the same. You can kind of see we've cut out the rest of the lingering EV signals. We've cut out almost all of this 372-day spike now. So this is the plot that I showed you. This is the 4,000 PCs that end up distributed in radius to period space. So this is the plot.
Do you have an estimate of how many of those KOIs that you're throwing out when you're talking about the candidates are planets?
So we do. That's what I am about to talk about. So one of the things we need to know. So now we have our list of planets, but we don't know how complete that list is, and we don't know how reliable that list is. We need to measure these two things in order to turn these raw numbers into a current rate. We need to know how complete you are, how reliable you are. Okay, so what does that mean? So A to Earth, how common Earth-like planets are, can be boiled down fairly easily into two numbers. The number of real Earth-like planets in your sample, which is a measure of the false positive rate. So some of those dots on that plot weren't real. Some of them are fake signals that made it through. Divided by the number of stars around which you could have detected that.
Did you take off your name tag?
Oh, sure. Oh, but my microphone's attached.
Oh, okay. It's working.
That's why it wants it.
I could probably attach it to the first. Is that better?
Yes.
All right. Sorry about that. Thanks, Dan. Okay, so that's the number of stars around which you would have detected these things. So that's your completeness. How many did you miss? So there should be points there that we didn't see. How many did we miss? And that is a function of just the pipeline missing it as a function of signal to noise, it having enough signal to noise that the pipeline sees it, and also the fact that geometrically most of them don't fit. So there's two corrections that go in there. Okay, so visualizing what that means, here's a plot of completeness for the target Kepler 22b. So this is period, this is radius in Earth radii, and this is a map of how complete the pipeline would have been to additional planets in this system. So for short period things that were larger than 1.5 Earth radii, we were basically 100% complete. We would have found that planet in that system. And then as a function of signal to noise and window function, meaning we had to see through transits, you can see the signal to noise dropping off. So down here, a 500-day planet at 1 Earth radius, we wouldn't have seen.
But you wouldn't have seen it at all, transiting 3 times, so why isn't it 0?
So it does fall off to 0 basically here. So the 4 years of data turns into a 700-day max. So this is like the actual
3 times 400, 3 times 700.
2 and a bit times 700, because you could have a transit right at the start, and then in the middle, and then right at the end. But that's what these vertical lines are basically the period cutoff, and it gets folded into the signal noise. Okay, so what we do is we inject a bunch of fake planets. Around every target, most of the targets, I injected a fake planet. These are the parameters of the planets that I injected in period and radius. Red means it was detected, blue means it wasn't detected, and you can see the same fall off in detectability. So this gives us the ability to make that map, to turn the signal to noise of period into a completeness estimate. And we take those 45,000 ground truth planets, these are things we know are planets because I made them planets, I put them on the target star. And we give them to the RoboBeta. We say, hey, RoboBeta, making your automated decisions, how well do you do? And we can also use it to tune the RoboBeta and say, here's what you should be knowing. So here is what the RoboBeta finds on those 45,000 things that get recovered. So those are the ground truth things. So this is basically a proxy for signal to noise. And the pipeline has a detection cutoff of 7. So this is a proxy for the signal to noise, and this is the percent of the time that this injected signal gets turned into a planet candidate. So you can see for above about a signal to noise of 10, it plateaus at about 90%. So 90% of the time, your real planet gets called a real planet by the RoboBeta. This is actually a really strong function of period, even beyond the window function. But take it out now because it's a TCE, it definitely had 3 events. So now I've split it out into as a function of period. So for the short period things below, say 200 days, so the blue and orange and green curves, the plateau is more like 95%. But as you get to longer periods, 200, 400, 400, 500 days, this really starts to drop off. Now, because this isn't a window function effect, these are things that definitely have 3 transits, what this means is that one of those, or multiple of those questions that the RoboBeta is asking is penalizing long period things more than it should be, which is bad when you're trying to look for long period things. But everything we did was basically a trade in trying to let through as many planets as possible and keep back as much junk. So if you basically take this and slice it the other way, so now I'm collapsing it in signal to noise and showing it in period, this is the fraction of real things that I injected that got turned into PCs as function period. So this is just to show that period from. But we've measured it, so that's what means we can correct for it. We also need to inject false positives. We need to know what the RoboBeta called planets that weren't really planets. How many of those dots aren't real? And we did this 2 ways. One is that we just turned all the light curves upside down. So transits are negative going. They're always negative events. So when you take that light curve and turn it upside down, you shouldn't find any real transits anymore because you're looking for dips. Anything you do find, by definition, is one of your sources of noise that you're trying to remove. So we turned all the light curves upside down, ran it through the pipeline, and found nearly 20,000 TCEs. Now recall that if you turn them all up the right way, you get 34,000. So even if you blow away all the real transits, you still get 20,000 TCEs. That gives you an order of magnitude estimate of what's junk already, right? The other thing we do, okay, so that's just, this is to capture the systematic instrument effects, just showing you that these are things that happen basically yearly, which is a bummer. And it's due to the fact that the telescope has a 372-day orbit. The temperature of the telescope is changing all the time, which changes the focal width of your light on your detector, which introduces these voices on the CCD. And this is a close-up of what that looks like. And basically, you can see that it's kind of symmetric. Basically, the noise goes up and down, but if you were trying to fit a box to it, you could, if you tried. The other thing we did, besides inverting them, was to scramble them. So preserving the 1 year blocks of time, we then just reordered those blocks and searched again. So any real signals should get blown away by this as well, because you've made them incoherent by scrambling them like this. But these 372-day blocks should be preserved. And in fact, you get 24,000 TCEs if you do it this way. All right, so how well did we recover our false positive population? So remember, the black curve is the TCEs that really came out of the pipeline. The blue curve here is the TCEs if you run the inverted light curves, and the red is the scrambled light curves. So you can see qualitatively we're actually doing a good job of reproducing this shape. Neither technique on its own captures the whole population, but together they actually do a good job. So that was gratifying. And this is just an injected light curves, and don't pay any attention to the shape because this is a log and I injected them linearly. So how well does the rover beta do? 99.6% of the fake things, so when you flip them up or scramble them, get called false positives. So the rover beta is doing a good job of getting rid of the junk, but at the cost of real things. So only 85% of the things get called PCs. So what we had to do was a trade, basically. We could have made this number 99%, but then that number would have gone down, because to let more of the real things through, you have to let more of the junk. So it was a trade, and this is where we landed. Now, when you're doing it this way, when you're doing automated decision making, there's a cost. 44 real confirmed planets were thrown away by the rover beta, including Kepler 10b, which is one of the flagship planets out of Kepler. 106 signals that we know are false positives, because we've gone and done follow-up observations, were called PCs. And the thing is, though, that the catalog's designed for statistics. Your reliability on any individual planet is in question, but the point is we know in bulk what the behavior is. So if you want to find out an occurrence rate, you need to understand the bulk behavior of the individual behavior. Okay, so what does this mean? Here's what we measured in the end, our completeness and reliability as a function of period and signal to noise. What does this do to our occurrence rates? I just want to quickly jump through to that, because I know that's what people are interested in. If you apply our new completeness and reliability measurements to our previously measured occurrence rates, you get, so this is the previously measured occurrence rate by Chris Burke 2 years ago, which was that for 1 to 2 Earth radius planets in 50 to 200 day orbits around sun-like stars, FGK stars, 33% of stars had a planet in that box, 1 in 3. Now, what we have in the new catalogue, we have a measure of completeness and a measure of reliability, which is great. This number's gone down by about 30%. I'm just trying to guess. About 50%. So now instead of the number being 33%, it's somewhere in the 20% range. So instead of being 33, it's like 20. So the occurrence rate of planets in this box has gone down a bit. This is all kind of hand-wavy because we haven't done the whole thing yet. But just basing it on our previous occurrence rates and using our new corrections, this is what you get. But I know that you actually care about longer periods, that's 50 to 200 days. So let's go where it's truly dangerous and almost irresponsible to guess. Let's go from 300 to 700 days. Previously, what we had in this box was 30 planets. Now we have 20 planets. And importantly, now we have the completeness and reliability. So we're actually not that bad in completeness, but our reliability is garbage. Most of these things are not real. Only 40% of them are real. So we actually have a third as many planets in this box as we thought, which meant that our occurrence rate for 1 to 2 Earth radius planets from 300 to 700 days goes from being about 50% to being, somewhere between 0.1 and 0.3, so between 10 and 30%. So it's gone down. And that's because we know how unreliable the planet catalog is now, because we injected all these false positives. So they haven't come down by a lot. They haven't come down by an order of magnitude or 2 orders of magnitude. We're not saying that Earths aren't common, which was the previous assumption. Everything's just been subtly scaled back by like 50%. So factor of 2, but not a factor of 10. And again, we're going to do the whole thing. Sorry,
The
Tom.
vertical lines, no, the vertical lines.
Oh, these are other people's analyses of various versions of the Kepler data and what they've come up with. And this is basically to show that there's like 2 orders of magnitude spread in people's analysis of this box. And these are different techniques and different measurements of completeness and reliability. Some people made estimates of the completeness. Some people used their own pipelines and measured it. So this is to say there's a lot that we don't know yet. But the Kepler project, correcting the previous occurrence rates, we get something like 10 to 30% of stars like the sun have a planet 300, 700 days, 1 to 2 every year. So in summary, we're doing the full run through right now. And we think that the occurrence rates for small planets may be slightly smaller than we expected. All of these reliability and completeness products, all the light curves, all of the embedded light curves, all the scrambled light curves, all of the robo-embedded decision-making metrics are all available at the Exoplanet archive. So go play if you want to do it yourself, Charlie. And finally, Kepler's not the end of the road. We have K2 as well, and they have all these questions that we're really interested in asking. So my goal is to start doing occurrence rates with K2, and this is just a final plug. I'm hiring a postdoc to come work with me at Caltech on K2 occurrence rates. So if any of this is interesting to you and you're looking for a postdoc, please come and talk to me. The application deadline's in 2 days. So you have a little bit of time. All right, thanks.